Hi, everybody. I will let Peter Hoffmann introduce himself. He's going to tell you about PySpark. Take it away.
So, hello, everybody. So the next 30 minutes, we're going to talk about PySpark and the DataFrame API. My name is Peter. I work as a software developer at Blue Yonder. Blue Yonder is a provider of predictive applications in the European market. We have more than 100 data scientists and Python developers. And so I think we can say we are one of the biggest data science teams in Germany. We have offices in Karlsruhe, Hamburg, and in London. And yes, I'm going to talk about PySpark and the DataFrame API. I'm going to give a general introduction into Spark and PySpark, and then a little example of Spark and PySpark, and then I go on with the new DataFrame API. The DataFrame API was introduced with Spark 1.3. And I think it's a major improvement to Spark, and it makes explorative data analysis really more easy. So we'll see if you think the same. So what is Spark? Spark is a distributed general purpose cluster computation engine. It's written in Scala, runs on the Java virtual machine, and has APIs in Java, Scala, and Python. And it provides a streaming API, a batch processing API. Based on Spark Core, there's the mlib machine learning library, and it has another library for graph processing. The basic functionality of Spark is provided through Resiliant distributed datasets. I'll come to this later. And Spark Core is the computation engine, and it's responsible for scheduling, distribution, and monitoring of tasks in a computation network on a cluster. So you can think of you divide a big computation task in small tasks, and Spark is responsible to distribute the small tasks on each computation node. If one computation node fails, Spark will reschedule the computation and afterwards collect all the results and present the results to the user. Spark is based on, or can run on Hadoop clusters. I think it's an improvement on Hadoop with a different focus, where Hadoop always runs only MapReduce jobs and always has to persistent the intermediate results to the hard drive or to an HDFS storage. Spark tries to keep everything in memory. It looks for data locality and tries to run computations when possible on each worker node, and tries to combine several computations to run them on the worker nodes where the data is local. So the core concept of Spark is the resilient distributed dataset. RDDs, they represent a logical plan on how to computate a dataset. So you start with an input dataset, and then you have a graph of computations which describe your end result. And then if you have the description or the logical plan of your computation, you can execute this plan, and Spark will distribute your computations on the cluster. The RDDs are fault tolerant, so the system can recover when node falls down or goes away. Then it will reschedule this intermediate computation on another node and collect the data afterwards. There are two basic concepts for RDDs. The first one is the transformation. That is, take one or more datasets, RDDs, combine them, or do a map or a filter or reduce on the dataset, and then the result is another dataset. The transformations are lazy, so the computation only occurs when you take an output actions. So that's the second type of operations. When you take an action on an RDD, then the computation is started, and the action either represents or presents the result to the user or stores it somewhere in a database or in an HDFS data store. Spark tries to pipeline computations when possible. So when you don't have to shuffle data between worker nodes, Spark tries to combine multiple computations on one worker node and only shuffles data between worker nodes when it's necessary. When you work with distributed file systems, Spark knows about the data locality of your data. So if you have large data sets that don't fit to one machine, Spark tries to run the computations where your data is. So it tries to minimize the network traffic and the load on your whole system. An RDD is, or a resilient distributed data set, is basically a collection of objects. It can be flat objects, table-like, or it can be nested objects. So it's possible to have more structured records. The lineage graph is the model of how your transformations fit together. And show how to build one RDD from another one. You have, as I said earlier, functions like map or reduce or filter, where you can explain how the flow goes for your data through the functions. There are three different types of transformations. They are element-wise, so they can be applied to chunks of data on one cluster. They are transformations that need to shuffle data, that need to move the data between clusters, and there are the output actions that combine the data from multiple worker nodes and represent the value to the user. So what is PySpark? As I said earlier, Spark is written in Scala and runs on the Java virtual machine. PySpark exposes the Spark API to Python. You have a small example here. You will always have a Spark context. That's the gateway to your Spark cluster. So you will run the context locally and then talk to the cluster. That's a simple example here, just taking a text file and searching for errors. The computation, you define your computation locally through the Spark context, but the computation then is sent to the Spark cluster and run on the Spark cluster. So how is the data flow in a system where you have to combine JVM code, Java code, Scala code, and Python code? So as I said, you have the local Spark context. You can fire up an IPython shell, an IPython notebook, or run a local Python program. It will then talk through Py4j to the Spark driver, which is implemented in Scala. And this driver talks to the cluster or to the worker machines. And then on each worker machines, there is normally per core one Python process, and the Spark worker on the worker machines talks through pipes to the Python process. So the common interface to work with Spark is the RDD. As I said, it's a set of partitions. There are atomic pieces in the data set. RDDs define a set of dependencies on parent RDDs. There are always functions that describe on how to compute RDDs based on its parents. And the Spark cluster has information about the metadata, about the partitioning scheme, and the data placement within the Spark cluster. When possible, the calculation is done on the partition where the data is, and the data shuffle is only done when necessary. So now I'll have a quick demo that you'll get a clue how the Spark, PySpark works. So, okay, at first some imports. As I've started the IPython notebook through the Spark server, we already have this Spark context. In standalone programs, I can create my own Spark context where I have to say, okay, where is my cluster that I want to connect to, and what's the name of my application that you can see in the logs, which application is running. Yep. So we'll start with a little example. Because I'm running Spark on my machine, I can access local files. Normally, you'll have a cluster with several machines and have a distributed data set, where you get the data from, but the result is the same. So what do we have here? We have a simple employees CSV with some employee numbers, some names, and the gender. If you want to work with text files, you can just create an RDD from a text file. The text file is read by lines. Now, as I'll show later, there is a CSV reader for Spark, but here we'll do a simple map where we split the lines by each record to get the data. So in these computations now is run on the Spark cluster, so that's not run in my IPython notebook. And only when I call take or take, that is get me one element, or collect, that is give me every element, then the computation is done and I'll get the result from the cluster. So I've splitted the first line and got the result back. Now, for example, if I want to get want to get an overview of the gender in my data set, I'll split the data set to the male or the female field and do a reduce by it and then collect it. So that's basically normally a normal map reduce code. So I get an overview. I have 197 male and 120,000 female in my data set. So now another one that's just to give you an impression about the API. It's a relatively functional API. So it's, I think the filter, the map, you should know these functions from Python. They behave the same. You can insert either a function or a lambda expression. So what I want to do is to get an overview of the surnames of the male people in my data set. So what I'll do is I'll filter for the male people. I'm grouping by the first name. Just have a look at it. So okay, what do I get when I do a group by? So I'll get a key and an iterable with all the results. So it's basically the same as you do in the Python group by. And now I can do a reduce to calculate the number of people for each surname. And then I'll sort them and have a look at them. Okay, that are the names with the number of occurrences. As you can see, that's the normal Spark interface. I find it rather or not that easy to do a quick data exploration. It might be good to write ETL jobs, but even then you'll have to work a lot with tuples and always have the tuples identifier, and it can become quite hard to maintain your program and get an overview of what's going on in your program. So that's why I think the PySpark DataFrame API, which I'm talking now about is a really improvement, because I think it makes basic data exploration much, much easier. So what's the DataFrame API or Spark SQL? They have kind of changed the label for the same stuff. So until 3.1.2 release, it was called Spark SQL. Now they are more talking about the DataFrame API. What is it? Spark SQL or the DataFrame API is a part of Apache Spark, and it extends the functional programming API with relational data processing, declarative queries, and optimized storage. It provides a programming extraction called DataFrames, and it can also act as a distributed SQL query engine. There's a tight integration between relational and procedural processing through the declarative DataFrame API. You can always mix the RDDs with the data frames and take the computation style you like most, or the computation style that fits best to your problem. And it also includes a catalyst, which is a highly extensive query optimizer. So what the DataFrame API or the Spark SQL tries, it just builds a tree of your computation and then tries to optimize the execution as you know it on SQL query optimizers. And the DataFrame API can perform relational operations on external data sources, and Spark supports all data sources that Hadoop supports, and even some more. So what's a data frame? A data frame is a distributed collections of rows, and they are grouped into columns, and the columns are named, and they have a schema. And there are some high-level APIs for common data processing tasks like projection, filtering, aggregation, join. The data frame keeps track of metadata. You can do sampling on your data set, and you can add user-defined functions to the SQL queries. As with RDDs, data frames are executed lazy. So each data frame object just represents a logical plan on how to compute the data set, and it's not computed until an output operation is called. The DataFrame API is available in Scala, Java, and Python. They share the same implementation. And what I really like about it, the query optimizer runs your query and generates JVM bytecode. So even if you write or define your computation in Python, the end result will be executed as on the JVM and has the same execution speed as when you use the Scala DataFrame API. Because normally, if you only operate with the normal Spark stuff, the Python version of a program is always 2 or 3 times slower than the Java stuff. And with the DataFrame API, the speed is the same. And I think that's a big improvement. So you can think of DataFrame as an equivalent of a relational table. DataFrames can be created through various functions through the SQL context. You can either load JSON files, you can load CSV files, you can talk to external databases, you can use the Parquet columnar format. So there are lots of different possibilities to connect a data frame to a data source. So what you do when you want to define a calculation, you have some domain-specific language where you can define functions for data frames. So if you're familiar with SQL Alchemy or with Pandas, I think you should already know what this is doing. I have a filter, I apply a condition to the filter, and I'll select some fields that I want to have. The nice thing, as you see here, you have always the 2 possibilities on how you want to interact with data frames. So you can use a plain SQL statement. But if you like to, you can use a more programmability one, like the second one. But both statements compile to the same source code, to the same Java bytecode. So as I said earlier, Catalyst is the query optimization framework. It's written in Scala. It takes advantage of Scala's pattern matching features. And that's, as I said, you get the same performance if you use the Python Spark DataFrame API or the Scala Spark DataFrame API. And the DataFrame API is even faster than the normal RDD Scala implementation. So you can talk to different data sources, CSV files, Parquet, columnar storage, can use or access external databases. You can use all Hadoop data sources. And what you'll do, you'll import the data source as a data frame in the Spark context, and then you can register them as temporary tables, and then you can use normal SQL statements to talk to them. Beside talking through Python or Java or Scala to the Spark SQL interface, Spark SQL also provides a JDBC driver, so you can connect through any JDBC application to your Spark SQL data sources. So you can add business analysis tools to Spark or use it from other languages that are not natively supported by Spark. One of the most used data formats for Spark is the Parquet data format. It's a columnar data format. That means it stores its fields in column-oriented order that has some benefits. So if you only want to select certain columns of your data, it's much more faster because it can scan through your column from one to an end and not has always to jump to the next row. And if you do analytic queries on a column-oriented data set, it's also much faster. You can store the Parquet files to local files, but normally you will like to store them in HDFS, and then the Parquet data gets partitioned into HDFS chunks. What are the supported data types for data frames? There are the normal numeric, string types, byte types, datetime types, but also you have complex types, so you don't have to deal only with flat data, but you can have nested data, you have an array type, you have a map type, and you have struct and struct fields. Your data frame always needs a schema attached to it. There are two possibilities. The first one is schema inference. If you have a data source that has some data types attached to it, or if Spark is able to look inside the data and infer the schema, then you can use schema inference. Here's a quick example. You have just a list of dicts. You create a data frame through the Spark context, and Spark automatically detects the right schema. You have a list of struct fields and a long type and a string type. The other possibility is to programmatically specify the schema. That's for data sources where you don't have a schema attached to it, like CSV files, or if you want to generate your data on the fly. What we do here, it's a normal table style, so you have a struct with a list of fields, and each field has a name, has a type, and has a value if the field is required or not. So before I continue with another example on how to use the Spark SQL and Spark DataFrames, here are the important classes of the Spark API. So it's the Spark context. It's the main entry point for the data frames and the SQL functionality. It's how you connect to your Spark cluster. It's the data frame itself, which is a distributed collection of data grouped into named columns. It's a column that's an expression in a data frame, a row that's a row of data in a data frame. Group data, you can do aggregations on data frames, and then you'll get the group data. And the types, as I said earlier, is how to define the schema. So we'll move on to the next example. To use the DataFrame API, you have to create a SQL context. It uses the normal context, but it extended it a little bit. In the first example, we'll have a look at some treats that I loaded. So they have a hierarchical structure. That's fine with Spark. Spark can work with hierarchical structures. So I'll load the JSON file. So it are only a handful of tweets, so it should be fast. And for JSON, Spark is able to automatically get the schema of your tweets. So we have a rather large one. It's from the Twitter API. So you can access rows or the fields in rows through the dot syntax. So a tweet has a user object, or the JSON has a user object, and inside it has a field name. So we can have a look at this. Now what we'll do, we'll register our data frame as a temporary table as tweets, and then we can access the data source through normal SQL statements. I'll first show you an explanation. So that's the execution plan on how to get the information we want. So what do we want? We just want the username and all the text from all tweets that are tweeted by Valentin. What we see, we have a projection, so that's the field we selected, and we have a filter condition, and we are working on a physical RDD. So now we should see some tweets. Oh, he even retweeted me, so that's fine. We can do the same through a programmable API, so not using basic SQL statements. And if we'll show the explain, we'll see that we'll have the same execution graph as we had with the SQL statement. So that compiles both to the same execution. And again, here we should see the 3 tweets. Yeah, so it's basically the same. You have always the 2 possibilities, either querying the data sources through SQL statements or querying it through the Python API. Now a little bit more complex example. I've choose CSVs with data. So why don't we have employees? We don't have them. Just a second. I've just deleted the employees files, but I'll get them back. One second, I need the header fields again. So we'll try again. Okay, now we have the employees back. So we have an employees file and we have a salaries file. So, and they connect to each other through the employees number. If we want to work with CSV data, we have to provide a schema. So as earlier, we have a struct type with the fields for the employees and the same for the salaries. Just execute it. So now I've imported both data sources to Spark. I've registered them as temp tables for the employees and for the salaries. So now let's have a quick look at the data. How big is the data? It's not really big data, but it's fine for the presentation. So normally if you do execution on data sources or data frames, the whole execution is always done from the first step to the last step. And if you run it again, it's calculated again. That might not be always what you want, and especially for algorithms that work on the same data set multiple times, you have the possibility to run a cache on a data source. So now the data source will be cached the next time I access it. So the first time it should take some time until the data is loaded, and from now on the data is kept in memory, and you see the access of the data is much faster. If you've added a data source as a temporary table, you can use it in normal SQL statements, but the SQL statement is only executed if you call an action on your result, like collect or take. So we see we have 179,000 male employees, and we can have the same query in Python style. It should get the same result and compile to the same JVM source code. We can do joins over data sources. You can even join different data sources, so you don't have to join two CSV data sources. You can have one CSV data source, one JSON data source, and maybe talk to one external database. That's no problem. We again call the cache method, so we'll get just the first data back. Will take them some time to calculate. So what did we? Yeah, that's the not so nice thing about Spark. You always get Java stack traces. Let's try it again. Maybe skip the cache. Okay, it seems like the driver program has collapsed. So again, try the join and get the first result. Now it should work. So what we do, basically a normal join employees with the salaries on the employee number. And now you can work normally on the join data, do a projection, get some fields, do a selection. So I only want to get the people who have high salaries. So now that's an overview of all the people with a salary more than 150,000 per year. You can do grouping. Again, you can use it as a normal SQL statement. That's the number of surnames in the data file. Or again, you can do the grouping through the Python API. So you basically say which field you want to group by, what method you want to group, and I've added a sorting to get the 10 with the highest number of surnames. You can do aggregations, again in SQL style and in Python style. There are two ways to define aggregations. You can either provide a dictionary with your aggregation key and the aggregation function, or you can import functions and then use the fmax. If you are familiar with SQL Alchemy, it's the same concept. And what you can do, you can add user-defined Python functions to your SQL context. So what I'll do here, I've only have the year when the people are born in my data set, and now I want to get the age of the people, so I can register a Python function in my Python notebook. The source code then gets distributed to the worker nodes, and I'm able to use these user-defined functions in my code on my worker nodes. And if we have a look at it, we should see that we get the age and the birth date. So that's calculated on the worker nodes. And finally, what I really liked when I played with Spark, and I have big data sets, so you can do the big number crunching on your Spark cluster, drill or boil down your data set to the one that is relevant to you, and then get your data back as a Pandas DataFrame. From there on, work with a Pandas DataFrame locally, and, for example, plot it or do something with this in your data frame. So I think they both fit very well together. Do the big number crunching, out of core, out of memory number crunching on your Spark cluster, and then with the reduced data set, work on with Pandas. So that was mostly of my talk. Again, a quick summary. So what do we have learned? Spark implements a distributed general purpose cluster computation engine. PySpark is a layer which provides the Spark programming API to Python programs. The basic building block of Spark is the Resiliant distributed dataset. Through DataFrames, you can work in a much nicer way on your datasets, and the DataFrame API allows the manipulation of DataFrames through a declarative domain-specific language. I've just started, or we as a company have just started with playing around with Spark. What we liked is you can easily connect different data sources. If you are familiar with Pandas or SQL Alchemy, you should immediately feel at home. What we don't like is the Python API sometimes lags a little bit behind the Scala API. And as you've seen, you are back in the world of JVM stack traces. That's not a nice world. If you work with plain Python RDDs, you have always an additional cost of serializing and deserializing your data sets. And what we hope is that Spark keeps its promise that it scales horizontally. And what we really liked with new DataFrame API is that it offers the same performance to Python and Scala Java. So we hope to continue with Spark, and I'll give another talk at the EuroPython about Spark, where I hope where I can present some figures and some numbers, how Spark really works with big data, because all we have done until now is running it on 1 or 2 servers, so not really big data. It has a nice API to play with, but I think if you're just working on one server, there are better Python tools and faster Python tools to work with data that fits on one server. So that's it. If you have questions, please start.
So, thank you, Peter. Questions?
Yeah, so you mentioned that you were using Scala on 1 or 2 servers.
Yeah.
And I'm really curious about the performance difference between Pandas and Spark when they're both applicable. Clearly, if you have 1,000 computers, then Pandas can't do anything. But on sort of the one computer case, I wonder if there's a performance difference between the two. Can you speak to that?
Also, I haven't done really benchmarks, but if you use the normal Spark API, then the representation of your data is a collection of Python objects. So, as you know, that's a magnitude slower than using NumPy or something like that. So I think if you're running on one machine, the normal Spark data frames will be much slower. I didn't do benchmarking with the DataFrame API, which compiles the stuff down, but I even think that they will be slower as NumPy arrays or something like that. So my recommendation would be if you be on one, so if your data fits on one server or on one hard drive, there are better tools to work with.
I would love to see numbers at some point, if maybe for the EuroSci-Pi conference.
I think at the
really
EuroPython we are now setting up a bigger cluster, and we're looking at it for production use. So then I'll have some numbers. I think so.
Cool.
Do you intend to use Spark only for ETL? So it seems a bit like that, or
No,
do you also plan to use it for your analytics workflow? And in this regard, do you see any chance to integrate it in your standard Python or PyData workflow with scikit-learn and stats models? Because my impression is a bit that it's feature-rich, it's a mighty tool, but it also disrupts the standard Python analytics workflow.
Yeah. What we are looking into, yes, of course, we are looking into the ETL workflow, but what is mostly important or interesting to us is the streaming mode that Spark offers, so that you can computate in a streaming mode on batches of data samples, because that's interesting for real-time applications, and that's what we hope to use it for. About integrating it with the normal Python machine learning toolkits, maybe I can tell you something more at the EuroPython, but at the moment we don't, or I don't know.
I have another question.
Yep.
So, you mentioned you are only running it on 1 or 2 nodes right now?
Yeah.
So did you also experience stuff like out-of-memory errors, which happen frequently?
Yes.
And any tips on how to deal with that?
Not yet. So we are not running it in production. We are just looking at the technology. I think you can really learn some concepts from it that are really good. We have to see how it works in production or in production-like environments. So at the moment, I can't give you anything.
Okay, thanks.
Just maybe a question regarding the data frame. So the commands are pretty much the same what you have with the Pandas data frame.
Yes.
And so there's nothing more that you can do with it. So if the data fits in Pandas and you can work with one machine, you're good.
Yeah, if the data fits, but Spark is not intended to use with data that fits on one machine. You really get the benefit if you have really larger data sets that you have to distribute on many machines. So that's just for the exploration of the API to use it on one server.
No more questions? Okay. Thank you again.